So I'm going to talk about bonds and L functions. Okay, so why am I interested in L functions, bonds and L functions? Because first of all, they appear in a lot of interesting problems, and a lot of interesting problems are reduced to bonding L functions. And second, I'm interested in this particular area because the kind of tools used to solve these problems, the bonds, to get bonds and L functions, use tools from different areas of mathematics: spectral theory, Riemann hypothesis for over finite fields, closed-domain sums, ergodic theory. There are a lot of tools that are used to solve these, attack these problems. That's it. They're from all over the mathematics. So that's the reason I'm interested in these kind of problems. Okay, so what are L functions? L functions are some analytic gadgets attached to some arithmetic geometric objects or automorphic objects. LSF is a product of some local factors, and each local factor has an expression like that: 1 minus alpha jp p to the minus s inverse, and so there are m factors there, so it's a degree m local factor. So when you take the products, it has a Dirichlet series expansion as well. Okay, so examples for the degree 1 examples. So we already seen zeta function. It has a Dirichlet series and is a degree 1 Euler product. And similarly, you have Dirichlet characters. You can have so there are functions on Z which are multiplicative and like periodic with period Q. So you consider LS chi's, which are Dirichlet series is the coefficients chi of n's. They also have Euler products, and this basically is the fact that Euler products of the fact that the Dirichlet series is equal to the Euler products is basically the fact that numbers are products of primes, and here it also uses the fact that characters are multiplicative. Okay, so characters are multiplicative and numbers are product of primes, gives you these expressions between Dirichlet series and Euler products. Okay, so now I'll move on to degree 2 L functions. So L functions. Okay. So the first example is L functions for modular forms. Here, delta z is a function on the upper half plane, which has this Fourier expansion tau of n exponential to pi n z, and it has this kind of it satisfies these relations. Tau of az plus b over cz plus d is some automorphic equals delta z up to cz plus d to the 12. This is the automorphic factor for every ABCD in SL to Z. So that's a modular form, and for that modular form, you have this Fourier coefficients tau of n. So using those Fourier coefficients, you can form this Dirichlet series, and it also the Dirichlet series, and you can also form this Euler product, and these two expressions are equal. The equality of these two expressions is more intricate. It comes from the fact that tau n's are multiplicative. To prove that tau n's are multiplicative, you have to you have to observe that this tau z satisfies more equations. It satisfies some eigenvalue equations. Tau z is a eigenfunction for some Hecke operators that we have seen in previous talks. Okay, so there are some parameters that you have for tau of z, those Fourier coefficients, and you can form the Dirichlet series out of those parameters. Okay, next example is a function for an elliptic curve. Y square equals x cube plus x plus b. A, b are integers, and some non-magnitude of the discriminant. So now you count points on this curve mod p. Okay, so that let's call that point number of points to be n e of p. So take this curve, count points mod p, so that those quantities are n of p, and from n of p you create these APs, which are deviations from expected counts, p minus n of p. Okay, now you can form this Euler products, 1 minus AP p to the minus s p to the minus 2s inverse. So it's a degree 2 Euler product. Okay, this is except primes that. Okay, you can this is up to finite number of factors. For other factors, you have to define using for ramified things you have to use. Okay, so essentially, for the elliptic curve, you have this local parameters that you get by counting points, APs, and using those APs, you can construct this Euler product, and this is the L function for the elliptic curves. Okay, and it's a degree 2 L function. So I have more examples. Okay, similarly, you have some things called mass forms, which satisfy some differential equations for some eigenvalue equations. They also have attached L functions. Okay, so there are more arithmetic L functions coming from Gavva representations, and the L functions coming from automorphic forms. Modular forms and the mass forms are the examples, specific examples of these automorphic forms. Okay. So these are examples of L functions. So you have local data attached at prime coming from either arithmetic geometry or coming from representation theory, and you form this global object. Okay, so what are the properties of these L functions? So the first property is that they have analytic continuation. The way we have written down the Euler products and Dirichlet series, they converge only for large real parts. Okay, but they can be continued continued to the whole complex plane. So this fact that they can be continued to the whole complex plane kind of indicates that there is a cancellation in this coefficients of the L function. That kind of indicates that already this L function has some group-like structure. Okay, and so also, like, if you just look at the Euler product and try to establish the analytic continuation, we don't have a way to do that. All ways to establish analytic continuations of even arithmetic geometric objects, we have defined them through just Euler products. So, but like, we have to show that they are somehow automorphic and establish analytic properties of automorphic objects through their integral representations. So although we have produced them from arithmetic geometry, so for instance, for elliptic curves, to show their analytic properties, we really have to show that they are the same thing as an L function of a modular form, and then analytic properties of these arithmetic geometric L functions can be deduced because they are the same. They are also L functions for modular forms. Okay. Next, so analytic continuation is one main property, and functional equation is like the next important property. For instance, zeta s satisfies some relation between s and 1 minus s with some extra gamma factors, okay, thrown in there. And this functional equation for a zeta function is basically Poisson summation formula. If you this is like one of the it's a trace formula if you guys see it the right way, and it's a very important tool in analytic number theory. So it transforms sums of a function on n of f at integers to sums at integers of the Fourier transform. Okay, so functional equation of the zeta function is like this. Similarly, there are functional equations for Dirichlet characters relating Dirichlet character at ls chi to L1 minus s chi with some extra gamma factors, and you also have these arithmetic factors that you see. There's q to the s over 2 kind of arithmetic factors. There is this tau chi over square root q, which is also an arithmetic factor. Okay, so in general, so you have a functional equation of this form. Lambda sf is some epsilon f times lambda 1 minus f bar. So this is, so you put in some gamma factors, you put in some arithmetic factors, and there is a number of modulus 1, which in the Dirichlet of L functions case, it is this Gauss sum, normalized Gauss sum. Okay, so functional equation is the second most important analytic property of these L functions. So if you want to control the size of these L functions, we have to. So L functions have all these parameters. They have these parameters. Dirichlet coefficients are their parameters. You have the parameters which are like in the gamma factors. There are parameters which are coming in the arithmetic factors in the functional equation. There are other. Okay, so there are all these parameters. You put them together and create a single object called the analytic conductor, which, so it has qf, it has T, it has mu f. All these are parameters related to the L function. You put them together, and this is called an analytic conductor. And an analytic conductor controls the size of the L function. So if you want to understand how big an L function is for different kinds of L functions, so this analytic conductor tells you how big the L function is. Okay, so these are probably the L functions, and the main problems in the field are, okay, the first one is Riemann hypothesis, is about zero distribution of zeros of these L functions. All these L functions are supposed to have non-trivial zeros only on the half line. And there are the second important problems are about the bounds and the coefficients of this L functions, the local parameters. They are called Ramanujan conjectures. For instance, the Sataka parameters are supposed to be absolute value 1, and the real values of these parameters of the infinity are supposed to be 0. Okay, and there are other main problems about the special values. The arithmetic geometric rank of, say, which is like are related to analytic ranks. For instance, for the elliptic curve, the rank of the model Weyl group comes from the order of the vanishing at the critical point. Okay, and more generally, we have this set of all L functions, different kind of L functions, and we want to understand how they are related. One we have from arithmetic geometry and automorphic forms, and there are different constructions. You want to understand how all this space of L functions are related. Okay, that's the main Langlands correspondence and the Langlands program. Okay, these are the big problems. Okay, now, okay, why do I want to study bonds? So I'll try to explain where bonds of L functions come up. So first, primes. So if you want to understand primes in an interval, I already stated this before. So this is reduced to, we have seen in previous talks, this is reduced to understanding the logarithmic derivative of the zeta function. That's because, okay, the way I see it, if you're more analytic, you see that intervals, to detect something is an interval, you use Fourier analysis. So you use n to the it's or exponential it log nth. So that's why this zeta s has come up. So Fourier analysis, okay, or multiplicative Fourier analysis called Merian transform. It comes up in understanding how this, detecting these intervals. So yeah, so you want to understand this relation. What does it mean for a prime to be in between x and x plus y? That is detected by this n to the it's, and then you transfer the problem to understanding this logarithmic derivative of zeta function. And to understand the log derivative, you need to understand the singularities of the log derivative. And we have seen that the singularities of log derivative are exactly at poles and zeros of zeta. So we want to understand the distribution of zeros of zeta. Okay. So, but the only tool that we have to understand the distribution of zeros is through like bounding zeta. So there's no way to access zeros of zeta other than doing something about just the sizes of zeta, different kinds of sizes of zeta. So that's why understanding bounds of on zeta is an important problem. So if you want to understand the primes in an interval, good at precisely, the more precise information comes from more precise information about zeros that needs bonds on zeta. Okay, so we need bonds on zeta, which are like individual bonds, like how big is zeta at some value. Also, we need bonds on averaged over some intervals called moments. Okay, so we need both bonds on individual values and some average values like moments. So these give you information about the distribution of zeros. That's the reason we are interested in studying these problems. Okay, that's for zeta. Similarly, if you want to understand primes in an arithmetic progression, that is related to log derivative of characters over sum over all characters. So that's why you want to understand the distribution of zeros of these characters as both as chi is varying. For different characters, how are the zeros of this function distributed? Okay. Okay. So okay. So now again coming back to zeta. So if you want to really understand, the best, we have seen that to understand to get prime number theorem, we need to have a zero-free region. We saw that we need to know that there are no zeros on the one line. But if you want more precise information, about the prime number theorem, the error terms and so on, we need like more precise zero-free region. The best zero-free region that we have today is due to Vinogradov, that he gets by bounding sums of this type. So zeta s can be essentially understood like is essentially of this form. Like if you can be approximated by sums of this form, sigma and n to the it. So to understand bonds on zeta s, we need to understand bonds on this sums of the form sigma and n to the it. So sum n to the it's in some interval. If you can bound that, you can get zero-free regions. From that, you can get primes. So how do you get bonds on these kind of expressions? So n to the it is exponential it log n. So if you approximate log n with some polynomials, okay, so some polynomial fn, so then exponential it log n is like exponential fn. So you want to understand sums of exponential it fn, okay. So these are what are called exponential sums, sums of e to the it fn. Their fn's are varying, so these are like some points on the circle. You want to understand what is the sum of these n quantities. So typically, they're all of absolute value 1. So the trivial bond is to say that the value is n, but you want to show that it's much smaller. So the techniques involved in bounding these exponential sums are like one of the deep tools in analytic number theory. There are Poisson summation formula, Weil differencing, stationary phase, Vinogradov mean value results. Recently, there have been introduction of this L2 decoupling, and efficient congruencing. These are like different kinds of techniques to solve, understand this one sum. So this one sum has a lot of meaning in it. It just if you try to bound the sum, you'll see that a lot of arithmetic appears in trying to understand this one sum. Okay. So next. To get primes in short intervals, like I said, to get primes in to find primes, we need to have a control on the zeros of zeta. And somehow, if you want to show that there are not many zeros in the critical strip, you want to understand the bounds on the moments of the zeta. Like yeah, okay. For instance, for this particular problem, the problem that we already the current understanding of primes in short intervals. The best bound comes from this fourth moment of zeta function. So we need to not only individual bonds, like the bonds like averaged over t of the zeta function are also important. Okay, so let's see. I want to show previously I said that the individual bonds involve a lot of arithmetic. Bounding these exponential sums involves a lot of arithmetic. I'll also try to show how bounding this fourth moment kind of problems has there are much more deeper tools that appear when you try to bound these zeta half plus it. So zeta half plus it has this expansion. So it's like a short sum of 1 over n to the half plus it. So you want to bound zeta to the 4, integral 0 to t. So if you plug that in and expand zeta to the 4, mod zeta to the 4, you get an expression like this. 4 variables for each of the zetas, and you have an expression like this. So we have seen such expressions in the previous talk. Okay. So in this expression, so there's an integral from 0 to t of ab over cd to the it, and that expression essentially is that integral is extremely small unless ab minus cd is small. Okay. I'm not telling you what small is. I'm being very vague, but so depending on the problem. So yeah. So in this expression, unless ab minus cd, this difference between ab and cd is small, the integral is very small. So the only cases the sum is reduced to cases where ab minus cd is small. Okay. So and then. So we are reduced to solving this equation, finding solutions to this equation, AB minus CD, AD minus BC, sorry, okay. AD minus BC equals H. So this, you notice, is like the determinant equation, and you want to count number of points satisfying this, integer points satisfying this equation. Okay. So this problem is solved using deep tools in spectral theory of automorphic forms, like the functions on H mod SL to Z. So to understand to count points on AD minus BC, we need to develop, one way to do is develop spectral theory and develop what is called spectral gap. Or another way to think of, more hands-on way to think of it, is that you can write counting points on this equation can be related to sums of this kind, which are called sums, Kloosterman sums. Kloosterman sums are these exponential sums, mx bar, mx plus nx bar over c. So these are exponential sums, and you are trying to understand the sizes of exponential sums for varying c. Okay, so and this is a very hard problem. So the spectral theory gives you bounds on such expressions, and somehow this problem that we got in trying to understand the moments of zeta, the solution comes from this spectral theory. So yeah, so we started somewhere and we landed at a completely different place. So yeah, so okay, yeah. So the theory of Kloosterman sums is one of most interesting aspects of the spectral theory, and yeah, if you guys are interested, you should really look into it. Okay. So in general, so to understand, so understanding moments and this bounds on this zeta function they help in like understanding a lot of aspects of these L functions, like zeros on the critical line, the gaps between zeros, a lot of other analytic aspects. So for instance, to understand primes in arithmetic progressions, as we said, we need to understand the sizes of the L functions, and the size of and that is related to understanding sums of character sums like this. N is in some interval x to x plus y, and we are summing over chi of n's. Okay. And as already Mark mentioned, this is so class number formula. So L value at 1 of this chi d is related to the class number. So if you bonding this L values transforms to bonding the class number. Okay. So bonding this L as f's in for different f's and in different families. So it's a very interesting problem. It's related to different arithmetic problems. Okay, the best bound that we expect. Okay, this is not so. Okay, this is not that precise as such, but like yeah, the Lindelof hypothesis says that L of the size of the L function is bounded by this conductor that I've written before to the epsilon. Okay, so this is a big open problem. Okay, let's see. Okay, so the size is this. We kind of believe that the size is much smaller than q to the epsilon for every epsilon. Okay, so but let's see what we can actually do. Okay, so this LSF can be written as a okay, can be approximated by a Dirichlet series with q terms pretty precisely. But we can do better. We can approximate it with square root q terms by using the functional equation. The functional equation transforms sums which are of the size x to sums which are of size q over x. So sums of size x are transformed to sums of size q over x, and you have sum over q. So all the sums can be transformed to so all the ranges can be transformed to sums over length square root q. Okay, so that's so we have this L function is approximately equal to this square root q terms of this sum of square root q terms of this Dirichlet series. Okay, so from this, so you want to suppose you want to bound, you want to know what is the size of this L. If lambda is like 1, like say it's small, okay, it's bounded by 1, then you can see that this expression, so that's like 1 is 1 over square root n, and n is ranging to square root q. So that gives you a bound of q to the 1/4. Okay, do you see it? So if lambdas are bounded, this expression helps you to see that L's are bounded by q to the 1/4. Okay. So this bound q to the 1/4 is called the convexity bound, which is like the trivial bound, and people call it a trivial bound. But yeah, okay. so we actually believe that it's q to the epsilon, but what we can do is q to the 1/4. So let's see what does going from q to the 1/4 to slightly smaller mean. Okay, so this any non-trivial improvement from q to the 1/4 is called, this problem of improving from q to the 1/4 is called subconvexity problem. Okay, so you want to show that instead of q to the 1/4, it's slightly smaller than q to the 1/4, like q to the 1/4 minus delta. So this involves showing cancellations in this Dirichlet coefficients, and that really has a lot of arithmetic information. It's not just some analytic gadget. Showing that there are cancellations in these sums has just like e to the summation and summations of n to the it, showing cancellation involves a lot of arithmetic. Here also it involves a lot of arithmetic information. For instance, there are a lot of big open problems have been solved by proving subconvexity bounds on these L functions. That is, showing that the L function has size better than what we can prove slightly. So q to the 1/4 minus delta. A lot of problems can be solved, like a lot of equidistribution problems, like quantum unique recursive problems from all over a lot of places can be solved using bounds on these, getting better bounds than q to the 1/4. Okay, so yeah, so the q to the 1/4 is like the boundary. So getting q to the 1/4 something smaller than q to the 1/4 means needs a lot of inputs from based on the problem, and you could see that it is a non-trivial problem because it has these many applications. Okay, so that's for individual bonds, and somehow if you want to bound moments, okay, in a family, so because we believe that each of the value of this L value is like q to the epsilon, the average value of any moment should also be q to the epsilon. So by establishing this these bounds of average values or asymptotics of this moments is for different kinds of L functions is a very active area now. So for instance, let's do. So if you want to understand the moment of L at say k equals second moment of some family, so that's basically summing over f and summing over lambda fn lambda m over square root m, and you're okay, that's squared. That's something is missing. That's squared. So okay. So it's sum over f, sum over n, lambda n, square root n squared. This basically is sum over f, sum over n, sum over m, lambda f n, lambda f m bar, so square root of n. Okay. So the moments, so at least for the second moment, you have expression like this. So summing over the family. Okay. So now you have a sum over f. So how do you execute such sum over f? Okay. This is an expression for the L value, and you're trying to sum it over some family. How do you do that? Okay. So so to execute sum over f, we need some kind of trace formulae. Okay. That allows you to capture some orthogonality of this coefficients. Okay. For the case of the family which is just in the zeta function, we are varying t. For that case, summing over t is like integrating over t, which gives you an integral of that form, and that we saw is like a just direct computation, and we see that amounts to cutting down the size of m minus n. It restricts size of m minus n. But if you are summing over the characters, it boils down to the orthogonality of characters, and it detects that m and n are the same mod n, mod q. And in general, for modular forms, you are summing over modular forms. You have these trace formulae which relate this side of the expressions to some Klosterman sums, and we need to deal with the theory of Klosterman sums to estimate these moments. Okay. So so different families have different features basically. So you have this moment, it's the same expression you start with, but when you're trying to sum over the family, different families have different kind of trace formulae, and we use this trace formulae to get handle on these moments. Okay. So so there are so the moments which are the main problems are subconvexity problem, bounding an L value to better than q to the 1/4, and the second problem is getting bounds on the moments of the L functions. So these are very okay. Again, they're interesting because getting handle on this help you to understand the zero free regions, zero density estimates, critical zeros, gaps between zeros, some equidistribution problems, and there are a lot of tools that I've used to solve these problems, like exponential sums, the trace formulae. So if you want to Riemann hypothesis over finite fields, spectral theory of closed-domain sums, and there are recent work by Akshay Venkatesh and other people so they input tools from ergodic theory and period integrals to understand the sizes of these expressions, and there are other technical tools called amplifiers that are used to understand these kind of expressions. Okay, yeah. So. Yeah, do you have any questions? Or?
I have a question about the shifted convexity problem.
Yeah.
So I do not know too much about it, but you mentioned there is some resource using spectral theory.
Yeah.
I wonder if do you know of any method coming from algebraic geometry, because it seems that you're looking at the nearby fibers of a curve and then counting points.
Yeah. So what do you mean by okay? The only so if you want to really establish the count, right? You can get like in the sense what kind of tools of algebraic geometry do you have in mind? So okay, so so counting integer points on this kind of surface, these varieties, I guess. So you can guess this main terms or the way they behave actually from algebraic geometry and like considerations of local global principles, but to actually show that it's the main term and the error terms are small. So most of this work is main terms are the easier things to get like expecting what happens is the easier thing, and in the sense that you just count solutions mod p and somehow raise it to solutions in Z. So that can be done. That gives you a main term. But there are these error terms that you have to take care of. And so understanding these error terms is basically the whole game. So the spectral theory does the closed-domain sums, showing that they are small, is basically in some sense showing that the error terms are small. So in many for whatever point counts that we did like we have before, it just somehow all of them reduced to dealing with this error terms, and they happen by different kinds of techniques. Where I don't know if algebraic geometry can deal with these error terms without. I mean it does deal with these error terms when you are counting points mod p, right? Like that gives for instance for elliptic curves y square equals. So we're counting points np. I said this is p plus ap. Okay. So this p is the main term, and you are interested in this error term. And algebraic geometry actually, I mean like this Delian and so geometry over finite fields gives you the error terms are actually gives that the error terms are small for counts on over finite fields. But if you want to count points over Z, I don't see a way to get handles on error terms from just geometry. I don't know.